So let's begin video number 3 of organic chemistry. Remember at the end of the last video I was talking about TNT, the explosive compound. Let's just go back and review it because I think I was rushing that at the end. But I hope you're getting this. Hope you're not sick of looking at my hands. When I watch these videos I see that you're getting really close-ups of my hands, so sorry about that. But anyway, why is this TNT again? Why do we have this numbering system? I've given you many examples here, but again, just to quickly review, when you have a organic compound, you try to find the parent structure. In this case, it's the benzene ring. And then you say, okay, it's not benzene, it's got some stuff added on it. We call those the substituents. They're additions to the benzene ring. So we have to do two things. We have to tell you what they are by giving you the prefix. And then we also have to tell you where they are by using a number. So the numbering of the ring is going to matter. It's going to matter if you go clockwise or counterclockwise in some cases. In some of these that I've given you, it doesn't because they have symmetry. But in this case, why is this 2,4,6 trinitrotoluene? So again, this is the toluene framework right here. That's the parent name. That's why it comes at the end. And then you have to say, okay, if that's the parent name, then that gets priority. That's the one position of the ring. So then I start numbering. Does it matter if I go this way or that way? Well, if that's 1, that's 2, 3, 4, 5, 6. That would be 2, 4, 6. At the 2, 4, 6 positions, I'd have something. If I go this way, I'd have something at the 2, 3, 4, 5, 6 position. It doesn't matter, but sometimes it does. So this would be called 2, 4, 6 dash tri. It seems redundant, but you have to do this. When you have 3 substituents, you have to say where they are with numbers, and you have to say that there are 3 of them. Give it the prefix tri-nitro. So this is a nitro group, NO2. Notice how I drew this one, what appears to be backwards. I did that because I want to tell you that the nitrogen is the atom that's bonded to the ring. If I drew it NO2 facing the other way, it would look like the oxygen atom is bonded to the benzene ring, this carbon, but it's not. The nitrogen is actually the atom that's attaching this carbon with that nitrogen, and then the other 2 oxygens come off of the nitrogen. But again, NO2 is a very high energy group, so a lot of explosives like ammonium nitrate, very common explosive as well, it's fertilizer, has the NO3 group. This is NO2, so organic molecules have NO2 as the nitro group. So that's how you name. Those are just some somewhat simple examples of how to name some derivatives of benzene. Again, I'd like you to try to memorize those. These don't really have to memorize, it's just bromine, bromo, nitro, nitro, and then the word benzene. But these don't have the word benzene in them. That's like water. We don't call dihydrogen monoxide. We don't call it that. We call it water. It's a common name. These are common names. So try to learn those as best you can. Now there are also a series of hydrocarbons that have benzene rings, but they have more than one benzene ring. They're actually fused rings. They're attached side by side. I want to spend a little bit on them because they're found a lot of places. And here's some of the common ones on this slide here. They're called polycyclic aromatic hydrocarbons, or PAH for short. Here's 3 of the real common ones. When you have 2 benzene rings side by side, we call it naphthalene. That's the smell of if you've ever smelled mothballs, that's the compound naphthalene. Now, notice how I'm drawing them. They're line drawings because it's just much quicker to draw them like this instead of drawing every carbon and hydrogen out. But I want you to be able to read these. So what would the molecular formula of naphthalene be? Well, it would be 1, let's just go around the rings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would be C10, if I did that right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 10. H, 1, 2, 3, 4, 5, 6, 7, 8. C10H8. It's very unsaturated. The saturated straight chain hydrocarbon, if you go back in a couple of videos ago, you saw that the saturated hydrocarbon with 10 carbons, this one here, was C10H22. So that's saturated. C10H8 means essentially it's had 14 positions taken away with double bonds. So I hope you're getting that, what I'm talking about here. I'm using a lot of new terminology, so I hope it's not too confusing because, you know, I'm just talking to a tabletop. I have no idea how you're comprehending this stuff. You're doing well on your quizzes, so I guess you're comprehending it pretty well. Another important hydrocarbon is called anthracene, A-N-T-H-R-A-C-E-N-E. I have no idea where these names came from, probably Latin and Greek words. This is a 3-fused benzene ring, so just add another one here and you get anthracene. Notice how I'm drawing them as well, either with the circle inside the ring or with the alternating single and double bonds going around the ring. Notice that if I single, double, single, double, single, double, I have to be careful where I put the double bonds. If I put 2 double bonds in a row, I would violate the rules of how carbon bonds. Each carbon, if you look carefully, has only 4 or 8 electrons around it. So either way is correct. Another common polyaromatic hydrocarbon is this one. It's got 4 fused benzene rings. It's almost like you took 2 naphthalene molecules and kind of offset them a little bit, and then fuse them together. You get this molecule called pyrene. It's sort of a pale yellow powder. They're actually all white powders, but this one has a yellow tint to it because it has some impurities and means it absorbs a little bit of visible light, so it turns a yellow color. That's why things are colored, because they absorb visible light. I use these a lot in graduate schools, so I know a fair amount about them. But they're all carcinogenic in real high doses because when you consume these in our bodies and our cells, they're oxidized to, they put oxygen atoms are inserted at certain places, and that can get into your DNA and cause damage and can cause tumors and things like that. So if you eat a lot of barbecued food, you actually are consuming these molecules. When you burn carbon at very high temperature, this is just another form of carbon when it's like any other fuel made of carbon. Many of these compounds are fluorescent and they might have medical applications. Fluorescent means that they absorb ultraviolet or visible light and then they give off a longer wavelength of light. That's a way that you can actually follow these molecules around inside a body or inside a cell because they give off colored light, so we can actually follow them with certain technologies. It's pretty useful. They're used in dyes a lot, in synthetic dyes, paints, and things like that. And believe it or not, they're actually found in outer space. So astronomers have actually detected these molecules, and this is just 3 of the common ones. There's probably 20 others that have sort of similar structures. But these have been found in outer space. How they got out there, I have no idea. But they're just formed, in stars, and the stars explode, and these are spit out into the interstellar medium. On Earth, they're found in coal tar, which is just a very syrupy liquid that you get when you distill or when you purify crude oil. Coal tar is just one of the fractions or byproducts of the distillation of crude oil, and this can be converted into coke. And gasoline and gases and things like that. The reason I know something about these polyaromatics is because in grad school I made molecules that look like this. I took anthracene molecules and I made derivatives of them by adding other benzene rings and nitrogen atoms and things like that. I did this to study what's called electron transfer. Scientists do this sort of research to learn more about things like photosynthesis, how plants take sunlight and they convert it into, and they make other molecules. But photosynthesis works on a mechanism where electrons are transferred in a molecule. It's almost like this is an electric circuit. Electrons can actually move from one side of the molecule to the other. So you can imagine that someday we might actually make electric circuits on an atomic level with molecules like this, where you can actually conduct electricity if you string a lot of molecules together like this. The benzene ring is found in all sorts of places. Even though benzene itself, the benzene ring is extremely toxic. This molecule by itself is dangerous. It causes leukemia in high doses. But when you combine benzene, when you make benzene into other derivatives, the toxicity drops quite a bit. And when benzene rings are found attached in other parts of larger molecules, they're actually useful. They're beneficial to us. They're found in proteins and in drugs and gasoline. Vitamins even have benzene rings in them. Food preservatives. 3 of the very common drugs you've probably used or heard of contain the benzene ring: aspirin, acetaminophen, and ibuprofen. Acetaminophen has a generic name, Tylenol. Ibuprofen is Advil. If you ever get a headache, you'll take one of these 3 things. I don't know. Aspirin is a sort of an old-fashioned medication. It's not so commonly used today because it can cause stomach ulcers because it's acidic. It's got this acid group on it. Acetaminophen and ibuprofen were synthesized partly for that reason. They were molecules that had the same effect as aspirin, but they had much better. They didn't have the side effects of causing ulcers. If you look at these molecules a little closer, when we get more into how to name these things, you can kind of see where pharmaceutical companies came up with these names. Like if you look at the generic name for Tylenol, acetaminophen, where does it come from? Well, if you look at the structure, the chemical structure of acetaminophen, you see that, you probably don't see it, but I'll tell you that one part of it is a phenol ring. That's a phenol ring, just that. This part here is an amine, and this part here is the acetyl group. So if you combine parts of those names, you get acetaminophen, acetaminophen. So that's what, they just combine the functional groups into a drug name. Ibuprofen, I can imagine they came up with that name, but if they look at the structure of ibuprofen, it's got a benzene ring, and on opposite sides of the ring, you've put this 4-carbon piece, and then over here you have this 3-carbon piece. Well, if this 4-carbon piece just happens to be called the isobutyl group, don't worry, I'm not going to make you generate these on quizzes, okay? This is a little advanced, but I'm just giving this to you for a little extra information. This is an isobutyl group. That's a benzene ring. When it's part of a larger molecule, has the name phenyl. And this is a 3-carbon acid. 3 carbons is based off propane, so there's the PROP. So you can see where they might have come up with this name if they combine this part of the molecule for isobutyl, this part, ibu, and pro for the propane part, propanoic part, and phen for the phenyl. They just changed the pH to an F. So, that's where some of these weird names you see for drugs come from. They're just reading chemical structure. They're just reading the functional groups and combining them into a name of a drug. Now the fun begins. Now we're going to talk about naming these things. Now this, you're probably going to have to run through this and listen to this a few times. Actually, before I get into the naming, I just want to talk about structures and how to recognize and draw different structures. But I have some of the chemical names written here. So don't worry if you're not understanding where I got these names from. I'm going to clarify with many examples where I came up with the name for this molecule, 2-methylpentane, and this is hexane. But not all hydrocarbons are straight chains like these. We can have, as long as you follow the rules of carbon wanting 4 atoms around it, and for 8 total electrons, you can make literally anything. So carbon is very good at bonding to itself, and it can make a wide variety of compounds. For these reasons, that's why there are literally tens of millions of different organic compounds known. And there's probably tens of millions of compounds that we haven't discovered yet or haven't synthesized in a lab yet, but they are all available. Isomers is a word for something that has the same molecular formula, but it has a different connectivity. The atoms are connected differently. If the atoms are connected differently, it's actually a different molecule with different properties. So we have to come up with a unique, different name for it. But we call compounds that have the same formula, but different structures, we call them isomers, and there's different types of isomers. These things here that are the same formula, but different structures, they're called constitutional isomers, or you could call them structural isomers. There are geometric isomers, which I'll talk about in a little bit, but these are structural isomers, meaning that they only differ in the structure. The bonding and everything is the same it's the same in the fact that they're all single bonds, but the carbon atoms are attached in slightly different ways. And so I'm going to show you some examples of how you can draw that and recognize that. So this is, if you look at this one as being hexane, 1, 2, 3, 4, 5, 6 carbons in a row, and look at this one, you can say, well, yeah, they both have 6 carbons and 14 hydrogens, but they're not the same molecule. When you're naming these compounds, you always try to find the longest chain of carbons. This one has 6 carbons in a row. This one, no matter how you look at it, either like that or like this, it's 5 carbons is the longest continuous chain. That's the key. Longest continuous chain is 5. I can't go like this and then jump to that. It has to be directly bonded. So if you're not seeing how this is different than that, then draw them out yourself and make sure you can see that they actually are different molecules. So we call them isomers of each other. If you look at this one, excuse me, versus this one, now it looks like they're different, but actually if you look carefully, they're mirror images of each other. If you reflect this molecule over this line, this mirror, you would get this molecule. Just flip it over and you get this one. You can see that if you just use your fingers to follow along. Here's a CH3. Go to the next carbon, it's got a CH3 and an H. Go to the next carbon, it's got CH2. Go to the next one, got a CH2. Go to the next one, you got a CH3. So they're identical molecules. They're both called 2-methylpentane. So they're the same molecule. They're not different. You got to remember, I've said this many times, we live in 3 dimensions. So these molecules are not flat. They don't sit still. They move around and they vibrate and they bend. But if you take this molecule and just flip it over, you get this. This same thing here. This looks like it's this, but that's not quite the same as these two. Look carefully, you'll see that now this one has the CH3 on the bottom, whereas this one is on the top. But I can convert this one into this one if I just take this one, and you can imagine just rotate it around a point and just rotate it 180 degrees. You'll get this. The CH3, if you rotate it 180 degrees, will now be on the bottom. The H, which is on the bottom here, if you rotate it 180 degrees, will now be on the top. This methyl will map onto that one, and this 3 will then map onto that. So you're rotating 180 degrees. So this takes practice. Don't think you're going to just get this right away. If you have a very good visual ability, you might find this rather straightforward, but a lot of people don't. So that's why organic chemistry is always like a nightmare class for students. It's really tough because you got to use these tools and these ways of using your brain and eyes in a way you've never done before. So they're the same molecule. Now, if you go to this one, this one comparing these two, I think is the easiest. Even though I've kind of drawn over them in red ink, but I just wanted to show you that if you look at this molecule carefully, you'll see that no matter how you look at it, the longest chain of carbons is 5. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. You don't always have to draw the longest chain horizontally. The longest chain can be bending in any direction. It can go this way, it can make a left, go up, it can go down. I'm just giving you examples here where the longest chain is horizontal, but it doesn't have to be. But this one is 5, this one is 4. No matter how you look at it, no matter how many times you try to find the longest chain, 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, 3, 4, 1, 2, 3. No matter how you look at it, the longest chain you can get is 4. So clearly these are not the same compound. And then if you look even more carefully, you'll see, yeah, this one has a 5-carbon longest chain, and then it's got 1 carbon sticking off of it. That's why when you're doing these practice problems on your own, you should circle the longest chain, and then you can kind of see whatever is outside the circled area is a substituent. You have to name it with a number. So if you circle that one, you'll see, well, this one has 2 CH3 groups outside the circle. This one only has 1. This one only has 1 hydrogen sticking out of the circle. This one has 2. So clearly they're different molecules. They're isomers of each other. They have the same formula. All these molecules I'm giving you are C6H14. They're all isomers of each other, but they all have different names. These two, what's the relationship between these two? Well, if you look at this one, it's the same as this, C6H14. This one, 2, 3, 4, 5, only 5 carbons with 12 hydrogens. And notice also, I hope you're picking up on the fact that even though these aren't straight chains of carbon, they have kinks in them and they have things, branches. It's almost like you can visualize these as a tree. This is the trunk of the tree, and the things hanging off are the branches. This one and this one, which is the same, has 4 carbons in a row and has 2 branches, 2 substituents. This one only has 4 carbons as the longest chain, but it only has 1 substituent. So this one only has 5 carbons, but it always has, in all these cases, has twice as many hydrogens plus 2. 2 times 6 is 12 plus 2 is 14. 2 times 5 is 10 plus 2 is 12. These are all saturated hydrocarbons. They're all derivatives of the alkanes. But these are actually different molecules. So now that kind of explains the isomers of the alkanes. There's a special type of isomer. Actually, before I get to this, I want to give you an example that's actually from your textbook. So let's hold off on that part. Let me go to this problem here. So I cover it up so you don't see the answer right away. Let me get a piece of paper here. These have all been written on. Hold on 1 second. All right, let's get a piece of paper here. All right. Here's a typical sort of practice problem you can do. Can you draw all the isomers of hexane? This is number 9 in your additional exercises of chapter 12 of your GOB textbook. How many isomers are there? Well, there's really no way to know that, but if you follow this very systematic approach, you can figure it out. So you write out the molecular formula of hexane. It's got 6 carbons. 2 times 6, 12, plus 2 is 14. So all the isomers you're going to draw are going to have that formula. If they don't, you've done something wrong. Go back and check your work. So clearly the most simple one is going to be the straight chain. Now notice I'm going to start to draw these now as all as line drawings. So again, if you don't like the way I'm doing it, you're going to have to write these out yourself. CH3, CH2, 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 CH3. That's what that means. I can't stress how important it is for you to visually and almost imagine going from this structure to the Lewis structure, the molecular formula with the carbons and hydrogens all written out. You have to be very good at that. Otherwise, you're just going to be bogged down and it's going to go very slow for you. There's only one way to draw that molecule. There's 6 carbons in a row. So once you run out of ways to draw that, you think, okay, now what if I just cut 1 carbon off and drew a 5-carbon chain? So go to a 5-carbon chain, and how many can you draw? Well, imagine now drawing only 5, and they say, okay, now if I only have 5 carbons in a row, where can I put something that makes 6 because I need 6 carbons. So I can either put something here, here, or here. If I go to here, that's the same as that one. You got to think it's symmetrical. If I go to here, it's the same as that one. So there's really only 3 unique positions on a 5-carbon chain before you start repeating over. But if you put the 6th carbon here, you just get this again. So clearly the only different thing you can do is put a carbon on that one and a carbon on that one. And when you do that, you get these 2 new isomers. If you put the methyl group here, which I'm just going to draw as a line, that's actually a CH3, that's a CH3, you get what's called 2-methyl pentane. That's a typo there. That's P. That's a P. P-E-N-T-A-N-E. 2-methyl pentane. Or if you put it here, you get 3-methyl pentane. 1, 2, 3 at the 3rd position. There's a methyl group, CH3, and there's the parent chain. So again, the parent chain, the parent part of compound, is always named last. So those are the only 2 possible ways you can draw isomers of hexane that have 5 carbons as their longest chain. So then you say, logically, the only thing I can do now is to go to a 4-carbon chain. The only possible places to put something different on a 4-carbon chain would be put it on the end, but if you just put another carbon on the end, you go back to this, so that's no good. You got to think internally, inside the chain. I can put one here, which is really the same as there, but look what happens. If I put one methyl group on each of those places, I get this. And remember, I have to come up with C6H14. I'm trying to draw all the different ways, all the different isomers that have that formula. They all have to follow that recipe. So if I have 4 carbons as the longest chain, I need 2 more carbons, 1 there and 1 there. That's clearly different than all the other ones I've drawn. So that's called 2,3-dimethyl butane. Butane, because it's only got 4 carbons in the longest chain, that hydrocarbon with 4 is called butane. And then the only other way I can do it is put them on, instead of on different carbons, I put them on the same carbon, and I get this structure here, which is called 2,2-dimethyl butane. What I would encourage you to do is try this. Try drawing, this will really help you practice drawing all the isomers of anything larger. So try drawing it of, let's say, octane. That's C8H18. Try doing that. Now, as you get the number of carbons goes up, the number of possible isomers goes pretty high. I'm not sure how many isomers octane has. Probably, I'm thinking maybe almost more than 10. Just see, that would be good practice for you, though. But this is how you attack a problem like that. It's good practice for you to not only learn how to draw molecules, but how to recognize molecules when they're different, and how to recognize, use your 3-dimensional skills. Now, going back to the previous slide, or piece of paper here, we were talking about saturated hydrocarbons, alkanes, but you can also have a certain type of isomer, different type of isomerization, called geometric isomers. These things, like I said, these are called structural isomers because they only differ in the structure. Well, if you have an alkene, you have a special type of isomer. So what is it? Well, it's called geometric because it has to do with how they're arranged and how they look in 3 dimensions. So look at this one versus this one. This is a 4-carbon straight chain alkene, contains a double bond, but this one also is the same thing. It's a 4-carbon straight chain hydrocarbon that contains a double bond. You might think they're the same thing, but they're not. I might have to end this video soon. I'm at 30 minutes and my phone's been cutting me off at that point. So if this ends abruptly, I apologize. I'll continue on in the next video. But this molecule is different than this one. Why is that? It's because a double bond cannot rotate. This double bond, if I had a model, you could see it. You can't rotate around a double bond. You can rotate around a single bond. Single bonds can all rotate. So this methyl group can actually rotate all at once around that carbon, as this hydrogen can rotate. It's almost like the electron density is spinning. But this double bond is locked in place. You can't rotate a double bond. So when the two methyl groups are on the same side, they're stuck there. They can't rotate to give you this. You can also, you might think, well, why can't I just take this molecule, hold this still, and rotate this 180 degrees, and you get that. But you can't rotate around that double bond. So this is locked in place. It's almost like it's set in stone. This is set in stone, so to speak. You can't rotate this to go back to that. So these are actually different molecules with different names. They have the same name here, meaning that it's 4 carbons in a row for butane, but we put the ene ending for the alkene. But we also have to call it cis or trans. When they're on the same side, we call it cis, C-I-S prefix, usually written in italics. This is trans, meaning opposite sides. So in the next video, I will comment a little bit more on that as well.